So if we look at these two curves here too as well, all right, we have some diagonal lines and some flat lines, some plateaus. And you can see the plateaus are labeled A and B and C and D. So what's happening at those plateaus in the heating cooling curves? Maggie? Yes, so it's at that point, so it reaches, it goes from like, you know, I don't know, up here. Well, actually, let's try to describe what's going on with this. What state of matter are we at up here? Yeah, straight. Okay, so then letter A is describing what at that plateau? Condensation. Yeah, you're going from a solid or from a gas to a liquid. So with condensation happening, it's a phase change. Phase change. So then at that curve right there, at that diagonal, where are we at? Liquid. Good. And then at B, that is freezing, yes. And then finally, the last diagonal line down here at the bottom, solid. Okay, good. All right, so the plateaus represent phase changes. The diagonals represent just a solid, liquid, or gas. Sure. Yeah, absolutely. Yeah. Yeah, the phase change descriptions are the same for whatever substance. Okay. Like sublimation, deposition, all that sort of stuff. Okay. All right. Okay. So as we are heating stuff, our Q's are going to get bigger. As we're cooling, our Q's go negative. There's an issue that we would have calculating our Q's at different points in time. And if we go to the next page here, this is a great picture right here at the top, because this is going to show us what calculations we're going to do at different points in time on our heating or cooling curve. Okay, so as you see, the diagonal lines, what are we doing? MCAT, okay? On the plateaus, why can't we use MCAT? No temperature change. So we do delta T is 0, MCAT 0, but we know that's not true, right? If you got a pot of water on there, you want to keep it boiling, you got to keep the heat cranked up, right? So you got to keep pouring heat in. So heat is being gained by that system, all right? So in order to figure that out, we're going to use delta H of vaporization or delta H of fusion during those phase changes, because that's the amount of heat associated with 1 mole of that substance going under that phase change. Okay? Okay, so we got to use, here we're using Q equals MC delta T. These other ones here, we got delta H of fusion going. All right, now something to take note of here, if we are calculating stuff from, say, on this graph, it goes from negative 40 degrees all the way up to 130 degrees. In order to calculate the total amount of heat here, we would have to do 1, 2, 3, 4, 5 total calculations. To find the heat associated with that. Okay? All right, so that's as long as the problems can be. All right? They'll be like, all right, well, we're going to heat up water from negative 40 degrees Celsius all the way up to 130 degrees C. How much heat do we have to pour in for 200 grams of water? And then you just, here we go. Okay? We'll do one of those problems. And then that will be it. Because that's as hard as the problem can be. Okay? There's a couple other vocab words there. Take note of. There's sometimes when you have supercooled or superheated solutions. Okay, so that's when maybe you have something that is actually heated above its normal boiling point, but like in organic chemistry or things like that, some of those, if you're using very, very clean glassware, and the surface of the glass is really, really smooth. So there's not really a spot on that surface to form bubbles on for that substance that's in that glass. You might be able to superheat that substance, and then all of a sudden it's going to kick and boil all at once. And a lot of times it's like exploding out. It's like crazy. Okay? So we use little things called boiling chips, and they're just little tiny chips of porcelain a lot of times, and things like that. And they're unreactive, but it just gives a nice rough surface for bubbles to form on. Okay? So you might notice in a, I would notice this, but you maybe in a glass of pop, for example, a carbonated beverage that you have, and you pour it into a glass, you'll notice in different parts of the glass, the carbonation will be coming and forming at that particular point, and that's a part of imperfection on the surface of that glass. And bubbles will form there, okay? But if the glass is really brand new and stuff like that, it won't. So, but anyway, going. So let's do a couple problems, and then we can work some UT homework. So we've got them right up here. Diagonals, 2 equals MC delta T. On our plateaus, we've got our delta heat, or delta fusion, delta H vaporization times the moles, and we can go from there, okay? So we'll do one sample calculation of a plateau here. Start off with number 1. So we want to calculate the energy released or absorbed to convert 1 gram of liquid water at 0 degrees C to ice at 0 degrees C. So we're going from liquid to solid, right? So that means we got to, in order to calculate Q, we're in a phase change here. Since we're going from liquid to solid, we're going to use delta H of fusion. We're going to multiply that by the moles. So 1 gram of H2O, you got to find the moles of water. 1 mole of H2O. We've got 18.02 grams. Bless you. I got 0.0555 moles of H2O. I'm going to plug that in, okay? I don't know the value. So I'm just going to look at the front page there. Delta H of fusion is 6.02 kilojoules per mole. And we got 0.0555 moles. I already pulled out the calculator. What am I doing?
How do you know the delta H fusion? Is it always 6.02?
For water, it is. Right, but they give it to us right there in the front. Right, so they'll always give you those values. Typically, it's water. Still, they'll give it to you. Okay. They used to have it on your yellow periodic table back in a few years ago, but they don't anymore. Okay. So, but they'll always give you those values. The only one you'll have to know is the 4.184 for liquid water for specific heat. Yes. You got to know whether or not you're going. Fusion is for freezing and melting, and vaporization is for boiling, right? Going from liquid to gas, or condensating, going from gas to liquid. Okay. Good question. So delta H fusion is for freezing and melting. Yep. So, so here we're talking about, and Mr. Buat, you just sent me an email. Okay, so this is going to be from solid to and back and forth from solid to liquid. Okay, delta H of vaporization. You're going to use that when you're going from liquid back and forth between liquid and gas. Okay, sure. All right, and in this case, we're going from a liquid to to solid, so from liquid to ice, is heat being gained or lost there? Being lost. Yeah, very good. So that's why we're going to have a negative sign here. And we got point. I got 0.33. 0.0555 times 0.334. Okay, I didn't get that. That's kilojoules. Moles cancel, it's just kilojoules. Okay. Okay, now get ready. Hardest problem that we can throw at you. Yes, what, Maggie? Because we're cooling down, right? We're going from a liquid to a solid. So it has to lose heat. It's losing heat. Yes, it would. Because it's got to gain the heat. Okay? Or we understand that. Okay, that? Okay. All right, so for this one, what I usually do with these types of problems is I'll draw a little picture. So draw a little picture here. So I've got temperature over here. Got time on the bottom here. All right, so how much energy is needed to convert 0.5 kilograms? All right, 0.5 kilograms is how many grams of water? 500, thank you. Nice job. 500 grams, okay, of ice at negative, okay, so things are starting at negative 20 degrees C. We're going all the way up to 250, so 0, 100, okay? So we're starting at 20 degrees Celsius. We're going to start heating. We get to 0. It happens at 0. Plateau, we get a phase change. Then we got to heat again from 0 all the way up to 100. Plateau again. And we got to do going all the way to 250. So we got to go like all the way up to way up here. Okay, there we go, 250 degrees Celsius. Okay. All right, so we're running in that other problem up there. Okay. Now this is the deal. How many calculations are we going to have to do? 5. All right, so we got 1 right here. 2. 3, 4, and 5. Okay, so that's how I'm going to label them as we move down below here. All right, so for calculation number 1, what format are we going to use for this diagonal line? Allie? MC delta T. Okay, so Q equals MC delta T. So mass is 500 grams. We determine that. What's the specific heat of ice? Okay, 2.10 joules per gram, not degree C. All right, once again, that 2.1 on the front page there, they'll give them to you. Okay. All right, and then what's our delta T here? 20 degrees. Yeah, it's 20 degrees Celsius. We're going, our temperature initial is 20. Final temperature is 0. So 0 minus a negative 20 is 20. So that, if you do the delta T's correctly, that'll also tell you what direction the Q signs should be. But if you know we're heating, that means heat's being gained. Okay, if you're warming the substance up, you got to gain heat. Okay, so Q will always be positive. If we're cooling it down, Q is always going to be negative. All right. Okay, so what do we get here? All right, I got 21,000. You get 21,000 joules. All right, or we can call that 21.0 kilojoules. Right. All right, step number 2. Phase change. All right, okay, so we're going to use our formula of Q equals, and this one we're at delta H of fusion, time our moles of H2O in this case. we got to figure out how many moles of water we have that are in 500, how many moles of water are in 500 moles, and 500 grams of water. So 500 grams, 1 mole H2O, 0.02 grams. You guys get 7.7? Okay, so we got our delta H of fusion, which is 6.02 kilojoules per mole. We're multiplying that by 27.7 moles. All right, so what'd you get? $160. You got. I'm going to round that up a little bit. 167. What are the units? What? Kilojoules. Yes. Good. Yes. No, we got to add them all together. Yeah, we need the cumulative amount of heat for the whole thing. So we're gonna add them all together. Okay. I'm sorry, I didn't say that, did I? Yeah, we gotta take all these 5 steps and then add them together. Okay. All right, so third step. We are on another diagonal, so we're using Q equals MC delta T again. So we've got 500 grams still. Now we have liquid water, so we got 4.184 joules per gram degree Celsius. And what's our delta T? 100. Thank you, Ms. Green. Okay. 500 times 4.184 times 100. So I got 209,200. Or basically 209.2 kilojoules. Hey, step number 4. Almost there. So at step number 4, this plateau, we're boiling, right? So we got to use the delta H of vaporization times moles of water. So that is 40.7 kilojoules per mole times 27 point, we still got 27.7 moles of water. And so I ended up with 1127 kilojoules. All right, the very last one, number 5, another diagonal. So we're MC delta T one more time. 500 grams. Specific heat of steam is 2.01 joules per gram degree Celsius. And we're going all the way up to 250 degrees Celsius. So our delta T is 150. $500 times 2.01 times 150. So I got 150,750 joules, which is the same as 150.8 kilojoules. And then we add all those guys together. So 21 plus 167 plus 209.2 plus 1127. So I got 675 kilojoules, which if we round that to 3 sig figs, boom, 1680 kilojoules. as long as hard as I can make it. Okay? I can expect a question like this tomorrow on the quiz. What? It's front and back, 1 page. All free response. Oh, and you have those. Right, because that's all this lesson's on. Is this right here, heat and cooling curve. The rest of the quiz tomorrow is going to be on like delta H standard. Yeah, that stuff. Yep, like Hess's law. Delta H to the reaction. Yeah, products minus reactants give you delta H to the reaction. Yep. Yeah. Objective 6, 7, 8, 9, and 10 are all those. Hess's law is in there, right? Okay, it's that. That's what's on the quiz. So it's basically homework number 3. That's it. There's a couple. Well, there's one nasty Hess's law problem on there. That's tough, but on homework number 3. Well, we got the rest of the time to work through homework number 3. The rest of what you have on here are basically just like some multiple choice questions and stuff. To kind of get you familiar with that. I would look at that stuff prior to the test and whatnot, but for the quiz tomorrow, you should be good to go. If you can work the problem we just did, you're ready to roll. Okay?